Let's transport ourselves back. It's 1986.
Yeah.
You're a senior engineer. Maybe you're designing, I don't know, an aircraft wing, or maybe running fluid dynamic simulations on like a new engine manifold.
Right. Classic engineering problems of the day.
Exactly. You're dealing with what we'd now call a classic finite element analysis problem, FEA. Breaking down this huge physical challenge into thousands, maybe millions, of simultaneous computations, you need results.
Yeah.
And you need them fast.
Oh, yeah. That was absolutely the defining bottleneck back then. I mean, the sheer computational load for these problems.
Yeah.
It meant you faced this really stark choice, a binary choice, really, that just crippled your time to market.
Okay, so what were the choices?
Well, you could try and book time on a real supercomputer, a multi-million-pound beast like a Cray, maybe an IBM mainframe. But that meant submitting your job, getting in a queue.
And waiting.
And waiting. Days, maybe weeks even, for your slot, and then finally getting the output.
Okay, so that's option 1, slow. Option 2.
Option 2, you try running that massive simulation on your local workstation. Now, this workstation might be, state-of-the-art for graphics, for interactive design work.
But for the heavy computation.
Woefully insufficient. Absolutely. You'd maybe kick the job off late on a Friday and just sort of hope that it might be finished by Tuesday morning. Crippling delays were just the norm. It was accepted.
It really sounds like a massive capital expense versus a crippling opportunity cost problem. Either spend millions or lose weeks.
That's it, exactly. The whole engineering world was just desperate for something else, a powerful but, accessible solution, something that could bring near supercomputer power right there to the networked engineering team.
Okay, so imagine this. What if that solution didn't just bring the parallel processing power down to, say, a mini supercomputer price point? But, and here's the real kicker, what if it could run your huge, existing, completely unmodified Fortran code base?
Now that would be something.
Without specialist programmers having to rewrite a single line? I mean, that promise alone must have sounded revolutionary in 1986.
Oh, it absolutely was. It was the bridge, the necessary bridge between decades of scientific investment and all that legacy code, and the future, which was clearly heading towards distributed high-performance computing. And, that exact revolutionary shift is captured perfectly in the pages of our source material today.
Right. So today, we are doing a deep dive into the October 1986 issue of Advanced Graphics magazine. Now, this was published for Apollo Computer UK Ltd., so, okay, we have to acknowledge the clear pro-Apollo context here.
Of course, yeah. It's essentially their publication.
But even with that bias, the technological shifts documented inside are just foundational, absolutely foundational to the world we live in today. Client-server stuff, networked file systems, all of it.
Yeah, the perspective is Apollo's, but the trends were real. So our mission today is really to extract the 3 big technological revolutions that were kind of colliding all at once in that brief window, the mid-'80s.
Okay, what are the 3?
Right, so first we're looking at the commercialization and really the democratization of parallel processing, taking it out of the labs. Second, those intense network topology wars, the bus versus the ring structures.
Yes, Ethernet versus token ring.
Exactly. And finally, this immense sort of unheralded cost problem that was being tackled by technical publishing systems. Sounds dry, but it was huge.
Okay, 3 big themes. But we really have to start with the cover story, don't we? Because it gives such a striking, honestly, a really dramatic proof of concept for the power of this new tech they were pushing.
Oh, absolutely. The cover. So the front of the magazine, it features this high-resolution satellite image of the Chernobyl disaster site. Remember, Chernobyl happened in May '86.
Right, just months before this issue.
Exactly. The image itself was captured by the French SBOT-1 satellite. Pretty impressive for the time, 10-meter resolution.
Okay, but capturing the image is one thing. Making the data actually useful, that's another challenge, right?
Totally. To get maximum clarity, maximum sort of effective resolution, the Analytic Sciences Corporation, TAS-SC, they had to fuse 2 different images. A lower resolution multispectral image with a higher resolution panchromatic one.
Okay, sounds complex.
It was. This fusion process, it required this extremely compute-intensive algorithm, an adaptive linear predictor algorithm. I mean, this is precisely the kind of job that would just tie up a conventional supermini computer for hours, maybe even a whole day.
Because you're asking the machine to run thousands, maybe millions of complex calculations across this massive data set, all at the same time, essentially.
Exactly. Thousands of calculations simultaneously. And here's the technological punchline. The proof of power they slapped right on the cover. Running that incredibly complex fusion algorithm, The final high-resolution image was generated in, wait for it, just 2 minutes.
2 minutes, down from potentially a full day.
2 minutes. On the system Apollo was selling, which was actually an Alliant FX8, but Apollo rebranded it as their DSP9000 Compute Server.
Wow. 2 minutes. That kind of speed.
Yeah.
It's not theoretical anymore, is it? It's immediately transformative. It just shatters that old choice. Spend astronomical amounts of money or suffer crippling delays for critical, time-sensitive engineering work.
It proved the concept. It showed the path forward. So, yeah, let's unpack the architecture that actually allowed that 2-minute computation. The Alliant FX8, or the DSP9000 as Apollo called it. This really represents that first major revolution we talked about, taking parallel processing out of the research lab and making it, commercially viable.
Okay, so before Alliant came along, parallel processing was mostly, an academic thing, confined to universities and high-end research labs. Why was that? What was the big hurdle stopping it from going mainstream?
The massive obstacle was, it was software dependency. Plain and simple. See, parallel processing requires your applications, your code, to be broken down into these discrete chunks, right? Pieces that can run concurrently side by side across multiple processors.
Okay, makes sense. Divide and conquer.
Right. But think about the existing code bases. You had vast amounts of Fortran code out there. Fortran was the undisputed language, the lingua franca of scientific and engineering computing for decades, highly optimized for things like array handling, but fundamentally written for sequential execution, one instruction after another.
So if you wanted to use one of these newfangled parallel machines, you couldn't just run your old Fortran code.
Nope. Moving to a parallel machine meant you needed specialist programmers.
Yeah.
Experts who could go in and completely rewrite, or at least heavily adapt, basically restructure, those vast proving code bases. And that was just prohibitively expensive and risky. You're messing with code that works.
So the human cost, the expertise needed, the time that killed the commercial potential for those early parallel systems. You had all this potential horsepower, but no easy way to actually use it with existing software.
Precisely. You had this incredible engine, but no easy way to saddle it, as you say. Which brings us to Alliant Computer Systems. Founded in '82, bunch of ex-Data general engineers, including Ron Gruner, from Sullivan New Machine fame.
Right, that classic book.
Yeah, they apparently started without a super clear product strategy, but they were focused on commercializing academic work. And they took a really pragmatic path. They looked for a way around that painful rewrite problem.
And they found it.
They did.
Yeah.
Their big breakthrough came directly from the work of Professor David Cuck at the University of Illinois. Alliant realized the compiler. The compiler was the key.
How so?
They figured, what if we could build a compiler specifically, one that was compatible with the standard Fortran 77, particularly the VX extensions, which were everywhere? What if that compiler could analyze existing sequential Fortran code and automatically restructure it for parallel execution?
Whoa! Automatically, without the programmer doing anything.
That was the genuine killer feature, yes. And it wasn't just about finding simple independent loops in the code, the easy stuff. It was about deep analysis.
Okay, what do you mean by deep analysis?
Well, it had to look at complex, nested program loops. These are often where the most computationally intensive parts of scientific code live. And crucially, it had to determine the data dependencies between loop iterations.
Meaning, whether one calculation depends on the result of the previous one?
Exactly. If one iteration needs the result from the one before it, you can't just run them all completely in parallel, right? You'd get garbage. So the Alliant compiler was smart enough to identify those dependent sections, manage the necessary synchronization points automatically, and only then break the truly independent sections across the available processors.
Okay, that's much more sophisticated than just saying the compiler did it. They built in the intelligence to actually understand the structure of scientific code, and that gave users a genuinely painless way to get this huge performance boost.
Totally painless. And critically, it meant that the entire universe of existing third-party scientific applications, all written in Fortran 77 for VX systems, could instantly run and run much faster on their new Minisupercomputer.
And that VAX compatibility, that must have been huge for adoption, right? VAX was dominant then.
Absolutely massive.
Yes.
It meant instant trust, instant familiarity. The market didn't have to wait for new software to be written for the Alliant machine. They just had to plug in the DSP9000, recompile their existing code with the Alliant compiler, and boom, massive speed up.
Okay, let's talk about the actual hardware. The DSP9000, the Alliant FX8. You said it was positioned as a mini supercomputer. What did that mean in practice?
The positioning was really critical. They were aiming for a sweet spot. Performance significantly higher than standard super mini computers, especially for floating point math, which is key for science and engineering. But at a price point that, a departmental engineering group could actually afford, not just the central IT budget.
And what kind of raw power are we talking about in real numbers from 86?
Okay, so the system could be configured with up to 8 computational elements, CEs they called them. Each CE delivered a peak performance of 11.8 MFLOPS, that's mega floating point operations per second. And that was for either 32-bit or 64-bit precision, which was important.
So with 8 of them,
if you maxed it out with 8 CEs, you were looking at a theoretical peak of 94.9 MFLOPS and about 35.6 MIPS, million instructions per second. I mean, that kind of floating point performance was simply out of reach for traditional workstations or even general-purpose supermenace at the time.
Now, what I found really interesting reading this is the design philosophy. They didn't just, stuff 8 fast processors in a box and hope for the best, did they?
No, not at all. They were very clever about it. They clearly recognized the fatal flaw in many early parallel system overhead, especially operating system overhead.
Right. So how do they tackle that?
They separated the labor. They used 2 distinct types of processors. You have the CEs, the computational elements we just talked about.
Yeah.
Think of them as the pure athletes dedicated entirely to the heavy lifting, the vector processing, the number crunching, no distractions.
Okay, the athletes. And the second type?
The interactive processors, or IPs, these were essentially the system managers. The IPs ran the operating system, which was called concentrics, based on a Berkeley 4.2 UNIX. And they handled all the input-output, user interaction, memory management, network traffic, all that administrative stuff.
Oh, I see. So the IPs took care of all the OS housekeeping, freeing up the CEs completely to just compute. Why was keeping the OS off the CEs so critical for hitting that near 95 MFLOPS number?
Because every single time a processor has to context switch, stop running the application code to handle an operating system interrupt or deal with an I/O request, it messes up its internal cache, it introduces latency, it loses precious cycles. Now, if you're trying to run highly concurrent processes across multiple CEs and they're all constantly getting interrupted by the OS, well, that switching overhead, which is typically managed by software, would just quickly eat away, maybe even completely nullify the speed gains you were hoping to get from parallelization.
Right.
By offloading the OS entirely to the dedicated IPs, Alliant ensured the CEs could run flat out 100% focused on crunching those Fortran loops. Minimal interruptions.
Makes sense. And you mentioned synchronization earlier. Even with dedicated CEs, if you have multiple processes running at the same time, they need to coordinate really, really fast, right?
Yeah.
To make sure they're working on the right data, not tripping over each other.
That was the other huge hurdle they tackled, again, using custom hardware. If they tried to manage that coordination, the process control, the synchronization between CEs using standard software techniques like semaphores or message passing, the communication overhead would still throttle the system, even with the OS offloaded.
So more custom silicon.
Yep. They designed specific custom hardware logic to handle all the necessary coordination, the locking mechanisms, the communication pathways between the CEs, essentially operating at the speed of the memory bus. This ensured maximum throughput and minimal latency between those computational units. It was key.
Okay, so this machine, clearly sophisticated, not cheap, I imagine, but you said it was accessible. What was the price tag back in 1986?
The price range given in the magazine is pretty wide, between £125,000 and $1 million.
Wow, that is a big range. Depends on the configuration, I guess.
Exactly. Number of CEs, memory, disks, etc. But even at the low end, $125K, let's adjust that for inflation. We're talking roughly £475,000 in 2025 money. The top end, £1 million, that's about $3.8 million today.
Okay, still serious money, but compared to a Cray.
Exactly. Compared to the, $10 million, $20 million price tags of the true supercomputers of the era, it really did make high-performance computing genuinely available at the corporate department level or for university research group. It changed the economics.
And Apollo's particular genius here was integrating this powerful computational resource so seamlessly into their existing domain network, wasn't it?
Absolutely. Apollo already had this large, established user-based engineers, scientists, using their workstations. By adding the DSP9000 as just another node on the network, a specialized compute server, any user on any Apollo workstation could transparently send their big, complex jobs over to the server for processing.
Like sending a print job, but for computation.
Pretty much.
Yeah.
The user didn't need to know the details. Apollo estimated back then that about 25% of their existing customer base were serious prospects for this thing. It really established that client-server model specifically for engineering computation, moving the heavy lifting off the local desk and into this shared networked powerhouse.
Okay, so they solved the computation bottleneck. But now you've got these massive data sets, the FEA models, the CAD files, the simulation inputs and outputs. How do you get them to and from that powerful server efficiently? That brings us neatly to the next revolution, right? The network itself.
That's exactly right. The DSP9000 was a beast, but its real utility depended entirely on having a high-performing network infrastructure underneath it. Remember, design engineers needed instantaneous shared data access, shared resources, facilities that traditionally you only got on those big, centralized time-sharing mainframes.
And Apollo's whole system, their whole philosophy was built around their network domain, which, as you said, put them right in the middle of the big network topology wars of the
Oh,
mid-'80s.
yeah. This is a fierce battle, primarily between the bus structure, think Ethernet, heavily pushed by competitors like Sun Microsystems, and Apollo's own ring structure.
Okay, let's break that down. Bus versus ring. We need to understand the technical differences and why Apollo was so convinced their ring was superior, at least on paper back then.
Let's start with the bus. So, Ethernet. It uses a protocol called CSMAD carrier sense, multiple access with collision detection. The analogy the magazine uses, which I quite like, is an unprioritized crossroads, first come, first served, meaning any workstation, any node, just tries to transmit whenever it has data. If the network's busy, it waits. If two stations happen to transmit at the exact same time, bam, collision.
And then what happens?
Both stations stop. They wait a random amount of time, a random back-off time, and then they try again.
That sounds potentially chaotic, especially in a busy engineering environment where you might have dozens of users all trying to access huge files simultaneously.
It could be, particularly for predictability. The source material makes a point of saying that Ethernet performance degrades rapidly and critically unpredictably once your network utilization goes above maybe 30% of the theoretical bandwidth.
Only 30%? Wow.
Yeah, once you hit serious contention, lots of collisions, the actual throughput just falls off a cliff. And this lack of predictability, it had knock-on effects. It forced rival workstation vendors, like Sun, to rely heavily on having local swapping disks on every single workstation.
Yeah.
Because relying on the shared network for something critical, like virtual memory demand paging, where you swap bits of memory to disk, was just too risky if the network performance could suddenly tank unpredictably. You needed that local disk for stability.
Okay, so that's the bus of that on net approach. Random access, potential for chaos under load. Now, Apollo's domain network used a 12 Mbit token passing ring structure. Tell us why that design was supposed to eliminate the contention problem.
Right, the token ring. Think of it like a continuously moving underground railway. That's the analogy here. There's a small digital packet, the token, constantly circulating around the ring. Only the workstation currently holding the token is allowed to transmit its data packet onto the ring.
Ah, so only one station talks at a time.
Exactly. Once it's finished transmitting its packet, it releases the token to the next station downstream on the ring. This fundamentally eliminates collisions. No two stations can transmit simultaneously.
Okay, no collisions. And that leads directly to the core advantage they claimed, right? Predictability.
Absolutely. Because the transmission is sequential, orderly, and prioritized by position on the ring, heavy network utilization does not impair the predictable transfer rates in the same way it does with Ethernet. If you know how many nodes are on the ring, you can actually mathematically predict the maximum time it will take for the token to get back around to you. Response time is deterministic.
That sounds much better suited for demanding real-time-ish engineering tasks.
It was argued to be, yes. Plus, the ring topology could generally span greater physical distances than early Ethernet coax cable. The magazine mentions up to 1 kilometer with coax, and over 2 kilometers using fiber optics, which was becoming available. Great for large corporate sites or university campuses.
And we shouldn't forget the industrial context here. Wasn't General Motors heavily pushing token passing around this time?
Yes, absolutely. GM was backing its manufacturing automation protocol, MAP, which was based on token passing principles. That gave Apollo's choice huge credibility, especially in the industrial and manufacturing sectors they were targeting.
Okay, so better theoretical performance, predictability, distance, industrial backing. What about reliability? What happened if a workstation on the ring failed or someone turned it off? Didn't that break the ring?
Ah, good point. Apollo had a clever solution for that too. The network interface card on each workstation included a self-healing mechanism, usually a relay in the plug or the interface. If a workstation was powered off or physically removed, this relay would automatically close, completing the circuit and bypassing the inactive node, so the ring itself wouldn't crash. Maintenance was easier.
Okay, so theoretically, Token Ring looks pretty superior on several fronts, especially for the kind of high-demand, predictable performance needed by engineers using that DSP9000.
Okay.
So why? Why did Ethernet, with all its acknowledged limitations, ultimately win the network topology war? It clearly did win in the end.
That is the million-dollar historical question, isn't it?
Yeah.
And the answer really comes down to a combination of factors.
Right.
Standardization, complexity, and ultimately cost. Token ring hardware, managing that token logic, bypass relays. It was inherently more complex than the relatively simple transceiver logic needed for Ethernet. More complexity meant higher cost per connection. Ethernet, despite its performance limits, was simpler, therefore cheaper.
And standardization.
Ethernet, driven by companies like Xerox, Intel, and DEC, the TX standard, achieved broader multi-vendor consensus and standardization much faster than Token Ring, which remained more closely associated with specific vendors like IBM and, well, Apollo. Ethernet became good enough, cheap enough, and crucially multi-vendor compatible. It's a classic case of, pragmatic simplicity and market dynamics triumphing over theoretical performance perfection.
Interesting. Okay, so setting aside the physical topology wars, Apollo had another major ace up its sleeve with Domain, right? The software layer, the network-wide operating system.
Yes. This is where they really leapfrogged almost everyone else at the time. Apollo ran this blended OS environment, originally Aegis, later evolving into Domainix, which incorporated more standard Berkeley 4.2 UNIX components. But the absolute key, the magic ingredient, was the network-wide virtual memory demand paging.
Okay, unpack that. What did network-wide virtual memory demand paging actually mean for a user sitting at an Apollo workstation?
It meant total, utter transparency. The physical location of a file or peripheral like a plotter, or even that DSP9000 Compute Server, it was completely irrelevant to the user and their applications. You could log into any workstation on the domain network, and you could access any file, any peripheral, any compute server as if it were physically attached to your local machine.
How did that work technically? Were they copying huge files across the network all the time?
No, and that was the beauty of it. Data was generally left on the central shared disk servers. It was only transferred across the network in small, manageable chunks, typically 4-kilobyte pages on demand. Only when a specific part of a file or program was actually needed by the application running on your workstation. The system managed thousands of these tiny network accesses per second, making it feel seamless.
Wow. That must have dramatically simplified data management for large engineering groups. And cut costs, too.
Immensely.
Mm-hmm.
Because the network effectively acted as one large shared memory space, it made local disks on individual workstations largely optional. Many Apollo customer sites ran very successfully with just centralized disk servers, often serving, say, 10 or 12 diskless workstations per drive. Think of the cost savings, no disk drive in every machine, and the improvement in centralized data backup and integrity compared to having data scattered across dozens of local disks.
Okay, that sounds amazing within the Apollo ecosystem. But the broader trend was towards UNIX for portability. Networking UNIX systems together was still a challenge back then, wasn't it? This led to another conflict, the network file system battle. We see the source contrasting AT&T's RFS with Sun's NFS.
Yeah, UNIX was developed long before local area networks were really a thing, so adding network file access was kind of bolted on afterwards. And it led to this fundamental disagreement about how it should work, boiling down to stateful versus stateless system.
Okay, stateful versus stateless. What's the difference?
AT&T's RFS, the remote file system, was stateful. That means the server actively kept track of the state of every file being accessed across the network. It knew which client had which file open, how many times it was open, whether any file locks were applied. This maintained the strict file semantics that UNIX programmers expected, ensuring data integrity, but it was complex for the server to manage.
Okay, so RFS aimed for correctness, but was complex. And Sun's NFS, the network file system, which ultimately became the dominant standard.
NFS took the opposite approach. It was stateless. The server treated every single request from a client as completely new and independent. It didn't hold any persistent state information about which files were open or who was using them.
What was the advantage of being stateless?
The big advantage was error recovery. If a client machine crashed, the NFS server didn't have to do any complex cleanup of state tables because it wasn't holding any state. This made NFS seem much more robust and faster to recover from network glitches or client failures. But this speed and simplicity came at a significant cost.
Which was? The source material highlights a pretty critical weakness, especially for high-integrity engineering work.
Yeah, the cost was data integrity. NFS, in its early versions especially, failed to maintain some crucial UNIX file semantics that are necessary for reliable collaboration. For instance, it didn't properly guarantee atomicity for operations like appending to a file, meaning another process could interfere mid-append. It also lacked full, reliable support for things like Berkeley advisory file locks.
And the really notorious problem.
The most infamous failing, highlighted in the source, was that because the server didn't know who had a file open or was actively using it, one engineer could potentially delete a file while another engineer on a different machine was still writing to it or reading from it. There was little warning. This really undermined the ability to trust shared files in critical workflows.
Ouch. That sounds like a recipe for disaster in a complex design project.
It could be. So Apollo's own domain file system, DFS, it provided that necessary high-performance transparency and data integrity within the Apollo environment, thanks to the network-wide demand paging. But its big limitation was heterogeneity.
Meaning it didn't easily work with computers from other vendors.
Precisely. DFS was brilliant inside the walled garden of Apollo domain. But it wasn't designed to provide that same transparent file access across a mix of different vendor systems, SUNs, DECs, IBMs. That cross-platform capability was NFS's ultimate goal and its eventual strength. The sheer difficulty of creating a file system that was high performance, maintained perfect UNIX semantics, and worked across heterogeneous systems meant the industry eventually kind of settled for NFS, even with its known integrity weaknesses, primarily because of its cross-platform compatibility. Good enough won again, in a way.
It's fascinating how these trade-offs played out. So the vision of the 1986 Apollo network, as described in the magazine, it really was this highly functional, tightly integrated unit, wasn't it?
Oh yeah, it was a complete client-server vision, fully realized within their ecosystem. The example configuration they described paints a clear picture. You've got different engineering groups, say mechanical design and electronic design, all sharing the same physical network infrastructure.
How would they use it differently?
Well, the mechanical guys might use cheaper monochrome workstations for doing the grunt work of setting up a finite element analysis model. Then they'd ship that job off to the central DSP9000 Compute Server for the heavy batch processing. And then maybe they'd use expensive color workstation to visualize the stress results afterwards.
And the electronics guys?
Maybe they're doing VLSI chip design on other workstations, accessing the same network, same file servers. And all of this rested on these massive, for the time, centralized file stores. The article mentions 500 megabyte Winchester disk drives mounted in cabinets that could offer up to 2 gigabytes of shared storage. That was enough for even the largest engineering databases back in '86. It was a cohesive, powerful system.
Okay, so we've covered the raw computation power with the DSP9000, and we've covered the network that glued it all together, the domain system. Now let's pivot to that third revolution you mentioned, the one that maybe doesn't sound quite as glamorous as hitting 95 MFLOPS, but which apparently solved an absolutely immense and perhaps hidden cost problem: technical publishing.
Yeah, this is such a crucial but often completely overlooked area. Product documentation, user manuals, maintenance guides, parts lists, specifications, it had become this monumental bottleneck. Michael Bosworth from Context Corporation is quoted saying exactly that. When your documentation is poor or incomplete or delayed, it impacts everything else. Quality control suffers, your time to market gets stretched, product support costs balloon.
And this is where the cost figures mentioned in the source,
Yeah.
they just become genuinely staggering, mind-boggling, actually.
They are almost unbelievable when you first read them. A major aircraft manufacturer, unnamed, but presumably someone like Boeing or Lockheed, estimated the product lifecycle support costs, just the ongoing support costs of an average page of technical documentation, at somewhere between $500 to $2,000.
Wait, hang on. $500 to $2,000 per page.
Just for supporting it over the product's life. What on earth were they spending all that money on? That can't just be printing costs. No, not printing. It was mostly the cost of validation, consistency checking, and revision management. Think about it. You have a complex product, maybe an airplane or a large industrial machine. It generates tens, maybe hundreds of thousands of pages of documentation. Manuals, parts catalogs, wiring diagrams, maintenance procedures.
Okay.
Now, every time there's even a small design change, a part number changes, a tolerance is adjusted, a procedure is updated, you have to manually find and check every single instance where that information appears across potentially hundreds of different documents to ensure consistency. It was a manual, incredibly painstaking, and hugely error-prone process.
Wow. So basically paying armies of people just to cross-reference documents constantly.
Pretty much. And to really visualize the sheer scale of this absurdity, we have that phenomenal anecdote from the source about the Safeguard anti-ballistic missile program back in the 1970s.
Ah, yes, this is brilliant. Tell us about that.
Okay, so the Safeguard ABM system, hugely complex. The system specification alone was documented across multiple bookcases worth of manuals, thousands and thousands of pages. Now, how do you verify the internal consistency of all that documentation? How do you make sure Section 5 in Manual A matches Appendix C in Manual Z?
How did they do it?
According to the article, the program would literally rent a high school auditorium. They would take out all the documents, physically, hierarchically, across the auditorium floor, and then the actual design teams, the engineers, would have to walk around manually comparing sections, verifying cross-references, checking structural consistency, making sure everything lined up.
They were using highly paid, incredibly valuable missile defense system engineers as human comparison software. Walking around an auditorium floor, the opportunity costs alone, renting the space, tying up dozens of experts for days, maybe weeks, just to manually check that document A agreed with document B. It must have been astronomical.
It was a validation exercise worthy of Rube Goldberg, wasn't it? Utterly absurd, but apparently necessary given the tools they had. And this level of absurdity, this massive hidden cost, is precisely what drove the demand for integrated technical publishing solutions, like the Interleaf Workstation publishing software, or WPS, which ran beautifully on Apollo workstations.
Okay, Interleaf. What did it bring to the table?
Huh.
It offered a powerful WYSIWYG environment, right? What you see is what you get.
Yeah, WYSIWYG was a big part of it. It meant technical authors could actually see the complex page layouts, the fonts, the integrated graphics on the screen as they worked, interactively. Much better than typing obscure formatting codes into a text file and then waiting hours or days for a typesetter to produce a proof copy. But the real genius of Interleaf, the thing that tackled that $2,000 per page problem, was integration.
Integration with what?
Integration with the engineering data itself. The case study mentioned involves a company called Shape Data. They were using Interleaf on their Apollo domain network to create the documentation for their new CAD product, Romulus D. And the key feature they leveraged was called inclusion by reference.
Inclusion by reference. Okay, sounds simple, but you're saying it was revolutionary. How did it fundamentally change that documentation workflow?
It created a live link between the document and the source design data. So graphics, things like engineering drawings, schematics, assembly diagrams, exploded views from the CAD system, they were not just copied and pasted as static images into the manual. Instead, they were referenced directly from the original CAD design database, in this case Romulus D.
Ah, I see where this is going. So if the design changes...
Exactly. If the mechanical engineer went back into the Romulus D database and updated the original schematic or drawing, the Interleaf document, the next time it was processed or viewed, would automatically pull in the revised graphic.
Wow, okay. That completely eliminates that entire costly, soul-destroying, error-prone manual rework cycle. No more frantic searching and replacing of diagrams whenever a design tweak happened late in the development process.
Precisely.
Yeah.
It shifted the focus from just document creation to document configuration management. The documentation was now dynamically linked to the engineering reality. It was almost guaranteed to reflect the latest design state, which is absolutely essential for safety-critical systems like aircraft, medical devices, or complex machinery. You cannot have outdated diagrams in those manuals.
Makes perfect sense. And Interleaf also helped with just the process efficiency for the documentation teams themselves, didn't it? It supported multiple authors working together.
Yes, it supported concurrent authoring. Multiple technical writers could work simultaneously on different sections or chapters of the same large manual, all operating within a common database environment on the network. Much better than passing around floppy disks or paper drafts.
And it handled all that tedious structural stuff automatically, too.
Right. That was the other huge time saver, addressing the manual validation cost. For large documents, the article mentions manuals exceeding 1,000 pages. The software automatically maintained and updated things like the tables of contents, the indices, cross-references between sections, lists of figures, even footnote numbering. Whenever an author inserted a new section, deleted a chapter, or made a significant structural change, Interleaf would ripple those changes through automatically. That kind of structural housekeeping was a silent killer of documentation time and a major source of errors when done manually.
So, putting it all together, while the initial investment might have seemed quite high, the source mentions around £35,000 for a complete electronic technical publishing system package, including the Apollo hardware, some illustration software, and Interleaf itself. That's about 133,000 pounds in 2025 pounds.
Yeah, not insignificant.
But the return on investment, especially for companies with complex products and large documentation sets, must have been almost immediate. Purely through eliminating those crazy manual validation exercises, reducing errors, and ensuring faster, more accurate time to market because the docs were ready when the product was.
Absolutely. It transformed documentation from being this necessary, painful, often delaying afterthought into an integrated, managed part of the overall product lifecycle. It genuinely saved companies millions, primarily by dramatically slashing that insane $500 to $2,000 per page support cost. It was a quiet revolution, but a hugely impactful one.
Okay, so we've seen the immediate commercial impact of things like the DSP9000 Compute Server and the Interleaf publishing system back in '86. Let's shift gears slightly and look at what the thought leaders of the time were predicting for the future of computer-aided engineering, or CAE. Dr. Richard Henschel from a company called PayApp Limited had a particularly insightful take, mentioned in the magazine, on this inevitable convergence of hardware and software.
Yes. Henschel's observation was pretty stark and quite prescient, actually. He noted that the cost of raw processing power, the price per MIPS, was just falling so incredibly fast. Hardware itself was rapidly becoming a commodity. The physical box was getting cheaper and cheaper, meaning the real value proposition was quickly shifting away from the metal.
Right. We often hear that classic prediction, hardware gets cheap, software is king, software suppliers will rule the world. But Henschel actually challenged that simple narrative, didn't he?
He did. He argued that hardware manufacturers don't just sell, silicon and plastic. They sell the immense amount of software effort that's embedded within their hardware product. Think about the operating system, the low-level device drivers, the network communication protocols, the specialized bitmap handlers for the graphics screen. All that fundamental software is what makes the hardware useful, and it's often what differentiates one hardware vendor from another.
Okay, so the hardware includes a lot of built-in software value. Where did he take that observation?
Well, here's his brilliant and I think really enduring prediction. He said that hardware manufacturers are constantly looking at successful software features or products out in the market. They identify functions that are becoming critical or popular, they buy the companies that make them, or they redevelop those functions themselves, and then they bake those functions directly into their chips, into the silicon itself.
Moving software functions into hardware.
Exactly. And once that function is implemented in silicon, the hardware manufacturer can then essentially give it away for free as part of the baseline hardware platform.
Wow. That creates a tough situation for pure software companies then.
It's the ultimate commoditization loop. Successful independent software houses, according to Henschel, face this constant, almost existential dilemma. They have to keep innovating, keep moving up the value chain to newer, more specialized niches. Before their previous big success, their bread and butter product, gets absorbed into the base level of the silicon architecture and suddenly becomes just a free, standard utility provided by the hardware vendor.
That's a really sharp insight. And you can see how that's played out over the decades since '86, right? Think about things like network interface cards eventually handling the entire TCP/IP stack in hardware, or graphics cards, GPUs, absorbing complex 3D rendering and even ray tracing functions that used to require specialized software libraries.
Absolutely. It's a prediction that just keeps proving true. Software eats the world, but hardware eats the most successful, commoditizable software.
Okay, so speaking of software innovation and trying to stay ahead, our sources also detail some proactive steps being taken back then to actually automate the software development process itself. PA Manufacturing Services had this thing called the Software Engineering Toolkit, or SET. What problem were they trying to solve?
They were directly tackling the growing difficulty and cost of producing modern, for the time, interactive, graphical, and importantly, portable software, especially software for those high-end engineering workstations with mice, bitmap displays, and complex user interfaces.
And their approach was?
Their core philosophy, as stated in the magazine, was all about structure, specification, and discipline, basically. Think before doing and specify before writing. They aimed to bring engineering rigor to the software process itself, and a key part of that was automating the highly repetitive boilerplate parts of building an interactive application.
Okay, let's look closer at one of the components. Their interaction handler, called InSet. How did that help manage the complexity of all the different input devices? The mouse, function buttons, the keyboard, to make things like testing easier.
Right, so InSet did something clever. It essentially buffered all those disparate input sources, mouse clicks, button presses, keyboard entries into a single standardized buffered command line stream.
Okay, why was that helpful?
It was critical because it decoupled the main application logic from the raw input hardware. Instead of the application developer having to write unique code paths to handle every possible mouse movement or key combination directly, the application only had to parse and react to a standard sequence of commands coming from this input buffer.
Ah, so it simplified the application code and testing.
It simplified testing immensely. Because the input was now this standardized command stream, you could test complex user interactions simply by feeding a pre-written script of commands into the buffer. You could simulate a whole user session programmatically without needing a human to physically click the mouse and type on the keyboard every time. Great for regression testing.
Clever. And they modeled the actual flow of user interaction using something called finite state transition networks. That sounds very structured, very engineering-like.
It is. Think of it like a specialized flowchart, but specifically designed to model the dialogue between the user and the software. Instead of just starting to code the application linearly, the designers would first graphically map out every possible state the application could be in, like waiting for command, editing object, displaying results, every possible user action, like click save button, type coordinate, select menu item, and crucially, every permitted transition between those states triggered by those actions.
So you'd have this visual map of the entire user interface logic.
Exactly. A formal graphical definition of the user interaction flow. And defining it this way, up front, allowed them to bake in some pretty sophisticated features very early and consistently.
Like what?
Well, for example, things like security checks could just become conditions on the transitions in the network map. If a particular user lacked the required security level to perform an action, the map simply wouldn't include a valid transition for that action from their current state. The option effectively wouldn't appear to exist on the menu or wouldn't be accepted from the command line.
Okay, makes sense. Any other features?
It also made it easier to implement things like automatic command abbreviation analysis, letting users type shortened commands or even building in a full basic macro language, allowing power users to create their own complex command sequences or automate repetitive tasks, all managed through this state network model.
Okay, that's the modeling part. But the real time-saving magic was supposedly in another module, right? Skelgin the skeleton generator.
Yes. Skelgin was the automation core of the toolkit. It took that graphically defined finite state transition network model, that map of the user interface, and it automatically generated the underlying skeleton application code.
What did that skeleton code include?
It included all the necessary boilerplate stuff, the code for handling the input buffer from inset, the menu structures, the basic error trapping, the state management logic based on the network diagram, essentially all the repetitive structural code that manages the user interface and input flow. And the best part was, this generated skeleton code would compile and execute immediately.
Ah, so instant runnable prototype.
Exactly. It allowed for incredibly rapid prototyping. The developers could define the interaction structure graphically, hit a button, get working skeleton code, and then just focus their efforts on filling in the specific application logic, the actual computational meat within that generated framework.
And this is what allowed PA to claim that huge reduction in development time, right? Up to 70%.
That was the claim, yes. By removing the need for engineers to manually write and debug all that tedious, error-prone structural code for the interface and input handling, they could concentrate purely on the unique, value-adding computational content of their specific application. It was a significant step towards automating software construction in the mid-'80s.
It's fascinating, though. Even while this sophisticated level of software automation was being pursued, the industry was still grappling with incredibly basic issues of standardization, especially in computer graphics. The Answer Board Q&A segment in the magazine highlights a really fragmented landscape there.
Oh, very fragmented. It's quite surprising looking back. In 1986, according to the source, only one international standard was really properly accepted and widely used for writing graphics software. GKS, that's the graphical kernel system.
And GKS was primarily for 2D graphics.
Yes, mostly 2D. It provided standardized functions for drawing basic primitives like lines, polygons, text, setting colors, defining coordinate systems, basic clipping functions. Foundational stuff, but limited.
But the cutting-edge engineering work, the CAD/CAM modeling, the scientific visualization, that increasingly needed 3D capabilities, didn't it?
Absolutely, which brought everyone to the major competitor, or alternative, standard. PHIGS, the programmer's hierarchical interactive graphics system. PHIGS was inherently 3D from the ground up. And crucially, it was based on a structured hierarchy of graphical objects. You could define complex assemblies made of subassemblies, which was much better suited for complex CAD models than GKS's relatively flat, unstructured approach.
Okay, so PHIGS was better for 3D and structure, but was it compatible with GKS?
Nope. Fundamentally incompatible. They had different conceptual models, so software developers and engineering companies were basically forced to choose sides.
Yeah.
If you wrote your application using GKS, it wouldn't easily work with PAGS concepts and vice versa. This really limited the portability of expensive engineering software.
A classic standards war, slowing things down.
Exactly. And it led to these sort of clumsy attempts to reconcile the two, like a standard called PHIGKS, developed in Germany, that tried to bolt PHIGS concepts onto a GKS base. It just created more complexity and confusion.
And perhaps the most surprising omission, looking back from today, what about the basic elements of graphical user interfaces?
Yeah, this is pretty amazing. The source explicitly notes that in late 1986, there were no real international standards yet for fundamental screen interaction features that we just take completely for granted today. Things like windows, icons, menus, pointers, WIMP interface.
Seriously, no standards for windows and menus in 86.
Apparently not at the international level. ANSI, the American National Standards Institute, was reportedly working on something. But the reality on the ground was that every workstation vendor, Apollo, Sun, DEC, IBM, Xerox, had their own proprietary way of implementing and managing windows, icons, and menus. The basic look and feel and the underlying programming model for manipulating a screen environment could be radically different when you move from one vendor's machine to another.
Wow. So we had parallel processing hitting nearly 100 MFLOPS. We had sophisticated network virtual memory across the building. But the common graphical user experience, how you actually interacted with the machine, was still completely proprietary, fragmented, contested territory. Amazing.
Yeah, it really makes this deep dive into 1986 such a fascinating technological time capsule, doesn't it? Because now, with almost 40 years of hindsight, we can look back and pretty clearly judge which of those foundational concepts really aged well and which ones turned out to be, well, technological dead ends or just transitional phases.
Okay, let's do that. Starting with the clear successes, the things that endured. That Apollo Alliant DSP9000 model, the dedicated compute server, accessed transparently over the network, that completely validated the whole client-server architecture for demanding tasks, right?
Oh, absolutely, 100%. It established the fundamental principle that high-performance, specialized computational tasks should ideally be offloaded from the user's interactive workstation and handled centrally by a dedicated, optimized server. The workstation client handles the interaction, the server handles the heavy lifting. This is, it's the bedrock of modern cloud computing, microservices architecture, specialized hardware accelerators. Anytime you send a heavy request off to a specialized server or service for processing, you're using that same basic model pioneered by systems like the DSP9000.
And what about the software side of that? The goal of automatic parallelization of existing legacy code?
Still hugely relevant. That remains a persistent, you might even say holy grail, for compiler design and high-performance computing today. Okay, maybe Fortran isn't quite as dominant as it was, but the core principle, taking existing C++A or Python or whatever code and having the compiler and runtime system automatically optimize it to effectively utilize modern multi-core CPUs, GPUs, TPUs, all these parallel architectures without requiring heroic manual intervention from the developer. That's still a massive focus of research and development.
Yeah.
Alliant proved the concept was viable for scientific code way back then.
Yeah, the dream lives on. And the technical publishing revolution driven by systems like Interleaf.
Foundational. Absolutely foundational. The core principles they established, WYSIWYG editing, relative documentation environments for teams, automatic structure maintenance, TOCs, indices, and especially that concept of inclusion by reference, where your documentation pipeline maintains live links back to the original design databases. These are all absolutely central to modern technical documentation workflows, content management systems, and ensuring accuracy in regulated industries. They successfully identified and largely solved that multi-million-dollar documentation bottleneck. Those ideas aged incredibly well.
Okay, so those are the winners. Now, for the concepts that, well, didn't quite stand the test of time, that fierce network topology war, token ring versus Ethernet.
Yeah, Token Ring definitely lost that battle in the mainstream LAN market. Despite its clear theoretical advantages in terms of predictable performance and determinism, which were genuinely appealing for industrial control and some high-end uses, it just failed to gain widespread adoption beyond specific niches like IBM mainframe environments and those early MAP industrial networks.
Why?
Ethernet just won on cost, simplicity, and faster standardization. It got cheaper, it got faster, moving from 10 millipiece to 100 millipiece, then gigabit and beyond. And crucially, vendors developed switched Ethernet, which effectively eliminated the collision domain problem for most users, negating token ring's primary performance advantage. Ethernet became ubiquitous, while token ring faded away. GM's big commitment to MAP also didn't last much beyond the late 80s.
Okay, token ring a historical footnote mostly. What else didn't quite pan out as predicted? Dr. Henschel's prediction about storage? He was directionally right about RAM becoming crucial, but he wildly underestimated storage needs, didn't he?
Oh yeah, massively. He projected in the article that reaching 100 megabytes of RAM in a workstation, which he thought was not far off in 1986, would likely make local disk drives irrelevant.
100 megabytes of RAM making disks irrelevant.
That was the idea. More RAM means less swapping a disk, and while having more RAM is always helpful, thinking 100 MB would eliminate the need for local storage.
Yeah.
Well, it just shows how hard it was to predict the explosion in data size. 100 MB today is, barely enough for a web browser tab cache. Engineers now routinely deal with multi-terabyte data sets, huge simulation outputs, massive CAD assemblies, genomic data, machine learning models. Storage needs just exploded exponentially, far beyond what anyone had imagined in '86. So local disks, network-attached storage, cloud storage, it all remains absolutely essential, definitely not irrelevant.
It's always humbling looking back at predictions. Okay, let's end this section on a more fun note. Let's appreciate the cultural side of what this distributed computing power enabled. The magazine mentions the Midnight Movie Group at Apollo. That gives us a fantastic little anecdote about the company culture and the power of the domain network, right?
It's a great story. Michael Shuley and Jim Arvo, they were Apollo employees, and they formed this informal group, the Midnight Movie Group. Apparently, they used their spare time, often literally late at night, hence the name, to tap into the enormous collective distributed computing power of the entire Apollo domain network, which across the company potentially included hundreds, maybe thousands, of networked workstations.
And what were they doing with all that networked power?
They were creating high-end, sophisticated computer-animated short films. They were really pushing the boundaries of 3D graphics techniques available at the time, particularly ray tracing. Ray tracing was, and still is, extremely computationally expensive. Rendering just a single complex frame could take hours, maybe even days, on a single workstation back then.
So they used the network like a giant distributed supercomputer.
Exactly. The fact that they could distribute the rendering workload for their films, like Fair Play, which was apparently a sequel to an earlier film called Quest, across the entire network of workstations, often running jobs in the background while people weren't using their machines. It just perfectly showcases the sheer practical power of the domain system for decentralized distributed processing. It was essentially one of the earliest non-academic examples of what we now call a distributed render farm. It really proved Apollo's mantra: the network is the computer.
That's brilliant. A great testament to the system's capability and the ingenuity of the employees. And just to sort of ground us completely in the hardware reality, the visual aesthetic of 1986, there's one final little hardware detail mentioned about the displays they were using.
I guess the monitors. To actually see the results of all this computation and design work, you needed good screens. The magazine highlights that Hitachi was offering a premium 20-inch color monitor back then, pretty big for the time, and it featured a very fine 0.26 millimeter dot pitch tube.
Why was the dot pitch important?
Finer dot pitch means sharper image quality. And critically, this monitor could deliver an astonishing resolution again. For 1986, a 1700 by 1250 pixels.
Wow, 1700 by 1250 on a 20-inch screen in 86? That's impressive. Higher than Full HD today.
It was very high-end. But engineers working on complex FEA models or intricate VLSI chip layouts, they needed that high resolution and large screen real estate to visually interpret the complex details effectively. Even if the heavy number crunching was being done remotely on that DSP9000 server, the quality of the visual display on the desktop had to keep pace. It was all part of the integrated system. Hashtag outro. So yeah, what an incredible deep dive that was. Back into the technologies that really define that pivotal shift from centralized mainframe computing towards the networked engineering workstations and servers that became the norm. We've really seen three major, tightly interconnected threads emerge from that 1986 snapshot, didn't we?
We really did. What were they, again, just to recap?
Well, first, you had high-performance parallel computation finally being democratized, brought out of the supercomputer centers and made accessible, largely thanks to intelligent compilation embodied by that Apollo DSP9000. Second, you had the rise of truly transparent, high-integrity networked file systems, like Apollo's domain, that made resource sharing seamless, even if the underlying topology wars were messy.
Right. And third,
That often unsung but hugely important revolution in technical publishing, driven by systems like Interleaf, which delivered crucial cost savings and efficiencies by integrating documentation directly with the engineering process.
it feels like that period, the mid-80s, really cemented so many of the fundamental ideas we just rely on, almost take for granted, every single day now. The basic separation of client and server responsibilities, the idea of automatic resource sharing across a network, the ability for engineers and designers to actually focus their time on design and analysis rather than spending weeks manually checking document cross-references or just waiting in line for mainframe time. The Apollo Alliant partnership, based on this source, they weren't just selling a fast box, they were selling an entirely new integrated workflow.
Couldn't agree more. And it brings us back to Dr. Henschel's compelling prediction, doesn't it? That relentless cycle where the most successful value-adding software functionality of today inevitably gets absorbed and commoditized into the baseline hardware of tomorrow. The source material back then even references that early dream of creating systems that genuinely aid rather than replace human thought processes, the grand promise of CAE and early AI.
Okay, so given that relentless speed of hardware development, its insatiable appetite for swallowing successful software functions and baking them into silicon, here's our final provocative thought for you, our listeners, to maybe chew on. What esoteric, maybe research-level software function or capability being developed today? Perhaps it's in complex AI model optimization, or maybe cutting-edge quantum error correction algorithms, or novel data compression techniques. What specialized software function will be the next big thing that hardware manufacturers successfully manage to put onto a dedicated, affordable chip and essentially give away for free on the desktop or in the cloud infrastructure sometime in the next decade?
It's a great question, because those core concepts established way back by systems like the DSP9000 accelerating specialized compute-intensive tasks through dedicated silicon, that pattern is perpetual. It just keeps happening at higher and higher levels of abstraction. We might well look back at today's specialized software research labs in, say, 2035 and clearly recognize the blueprints for the next foundational, free, hardware-accelerated feature that everyone just expects to be there.
Indeed. History doesn't repeat, but it often rhymes, especially in tech cycles. Well, if you enjoyed this trip through the pages of computing history and navigating the intense technological battles of the mid-80s, please make sure you follow or subscribe wherever you get your audio so you don't miss our next deep dive into another fascinating classic source. Until next time, keep your curiosity sharp.
And may all your legacy code parallelize automatically.